Hello students, welcome to my YouTube channel. In this video lecture, I am going to answer questions from sample paper number 1, RK BALI Navigation, 4th edition book. Even if you have any other edition book like the 5th one, the 6th one, the 7th one, no problem. The questions in those books will also be the same as the questions in the 4th edition book. In my previous video lectures, I solved the first 20 questions. In this lecture, I will be solving the next 10, that is question 21 up to question number 30. Let's start. Which one of the following statements is correct concerning the appearance of great circle, exception of meridians, on a polar stereographic chart whose tangency is at the pole? So remember, one very important property of the polar stereographic chart is that great circles are concave. Concave, that means bending away from the pole of projection. One exception is that if these great circles are very close to that pole of projection at very high latitudes, they may be considered straight lines. Okay, so higher the latitude, the closer they approximate to a straight line. Lower the latitude, closer they approximate to a straight line. They are all represented by straight lines. So correct option is option alpha. Higher latitudes means more of a straight line. Okay. Question 22. Distance q to r is given. Outbound speed, homebound speed is there. Safe endurance given to you. What is the distance from starting position Quebec departure to the point of safe return? So let's use direct formula. Distance to PNR, which is equals to endurance into outbound into homebound divided by outbound plus homebound. So endurance is 9 hours. Outbound speed is 436. Homebound speed is 485 divided by 436 plus 485. So distance to PNR will be equal to 436 plus 485, 921. 9 into 436 into 485 will be equal to 1903140. That is divided by 921 is 2066 nautical miles. Okay, 2066 nautical miles. This is a printing mistake. So it is 2066 nautical miles. Time to PNR. Just in case if they also ask you to find time to PNR, it will be equal to distance to PNR divided by outbound speed. So 2066 divided by outbound speed is 436 is equal to 4 hours 44 minutes or 284 minutes. Now, true course is given, task is given, winds are given, variation is given to you, deviation is also given to you. Calculate compass heading and ground speed. Now, you have been given true course. With true course, you can find true heading. With true heading and variation, you can find magnetic heading. With magnetic heading and deviation, you can find compass heading. So it's a three-step process. Let's first find true heading using CX3. So let's go to wind correction table option. True airspeed is 460. True course is 90. Winds are 360 at 100. So ground speed is 560 knots and true heading is 180. Correction. Wind direction is 360 at 100. Okay. So correction. Ground speed is 449. Double check the values. True heading is 077. So ground speed is 449 and true heading is 077. Now variation is 10 east. Variation is magnetic is least, means magnetic direction is less than the true direction. So 77 minus 10 is 0.67. Deviation is 2 degree. Let me check. 2 degree minus 2 degree. Okay, deviation is minus 2 degrees. Minus 2 degree means 2 degree west. So compass direction will be deviation west, compass will be best, compass will be more than magnetic. So 67 plus 2 is 0.69. So correct option, the closest option here is option A. Compass heading 069, ground speed 449 या फिर 448 knots. What is true altitude of aircraft if its altimeter indicated 6,000 feet where ambient temperature was minus 30 degrees Celsius? Correct. So true altitude is true altitude of your aircraft depends on two reasons, two factors: your pressure, atmospheric pressure, and temperature. Right. So if atmospheric temperature is warmer than ISA, okay, hotter or warmer than ISA, your true altitude is more than indicated altitude. If it's colder than ISA, your true altitude will be less than indicated altitude. So in this case, we are going to first find whether the ambient temperature given, the current outside temperature, whether it is more than ISA temperature or colder than ISA temperature. So step 1, ISA temperature at 16,000 feet should be how much? So it should be 15 minus 2 into 16, 15 minus 32, that is minus 17 degrees Celsius. What is the actual temperature outside? It is minus 30. That means outside air temperature is colder than outside temperature is colder than ISA by a value of minus 13 degrees Celsius. Minus 13 degree Celsius. Okay, so it's colder. So colder temperatures means if your outside temperature is colder than ISA, that means your true altitude is going to be less than your indicated altitude. Okay, by what amount? By what amount? So that is called temperature correction. The correction you are going to apply to indicated altitude to get true altitude. So that is the formula is 4 into ISA deviation into per thousand feet into per thousand feet. 4 multiplied by ISA deviation minus 13 per thousand feet. How many thousand feet? 16,000 feet. So multiplied by 16. So 4 into 13 into 16 is minus 832. So that means your true altitude will be indicated altitude minus the temperature correction. What is my temperature correction? Minus 832. So 16,000 minus 832, that is equal to 15,168. 15,168. So the closest option here is option alpha, 15,200. Question 25. Pressure altitude is given. Total air temperature. Now there is a difference between total air temperature and static air temperature. Static air temperature is the current ambient or outside air temperature. Total air temperature is the temperature measured by the temperature probe on your fuselage. Total air temperature will always be more than static air temperature because your aircrafts, your aeroplanes are flying at very fast speeds, because of which the relative airflow coming from the front gets compressed, and whenever it gets compressed, it gets heated up. So ultimately, the temperature that is sensed or registered by the temperature probe is little bit more than the static air temperature or the real air temperature outside. Okay, so we have total air temperature, we have Mach number, we want to find density altitude. Now density altitude is pressure altitude plus 120 into ISA deviation. Correct? So we know pressure altitude is 30,000. We must know ISA deviation. Now what is ISA deviation? It is outside air temperature minus ISA temperature. We can definitely find ISA temperature at 30,000 feet, which is ISA temperature at 13,000 feet is 15 degrees Celsius minus 2 into 30. So 15 minus 60 is minus 45. Now what is outside air temperature? We can use CXT to find out outside air temperature or static air temperature. So let's go back. So we have Mach numbers. So we will use airspeed option. Let's use airspeed option. Total air temperature is minus 10. Make sure all the units are in Celsius. So convert that unit first. So put 10, then hit the plus minus button. So minus 10 Celsius, Mach number 0.82, and pressure altitude is 30,000. So outside air temperature is minus 41 degrees Celsius. Static air temperature or outside air temperature is minus 41 degree Celsius. Minus 41. So minus 41 plus 45 is 4 degrees Celsius. Correct? So ISA deviation is 4. So 30,000 plus 480 is 30,000, 480. Closest option is the closest option here will be option. So if you take 118 into 4, option Bravo, 30,400 something. Okay. So density altitude. So this is how you do it. ISA deviation is nothing but outside air temperature minus ISA temperature. So outside air temperature we got minus 41. Okay. So if I use this 30,000, so density altitude I get 30,381. Okay, so option Bravo is the correct answer. By using this formula, we get 30,480 something or 472. In some formula states, instead of using 120 into ISA deviation, you can use 118 into ISA deviation. Still, the value will be around this much only. So the closest is option Bravo. When descending through an isothermal layer at constant CAS. Question 26. When descending through an isothermal layer at constant calibrated airspeed, what will happen to true airspeed? Now remember, they are saying that you are descending in an isothermal layer. So let's say this is that isothermal air mass. Okay. And you are descending in this air mass. Your plane is descending. Now atmospheric pressure, irrespective of irrespective of the temperature of the air, will increase as you come down to lower altitudes. Atmospheric pressure I'm writing it here. Atmospheric pressure at high altitudes is lower, but at low altitudes is higher. Correct? As you come down to lower and lower altitudes, atmospheric pressure increases in value. Now your calibrated airspeed is a function of dynamic pressure, nothing but your atmospheric pressure. Whatever dynamic pressure is registered by the airspeed indicator, that dynamic pressure will be shown to you in the form of calibrated airspeed, indicated airspeed, whatever. Right? So when you come down to lower and lower altitudes, forget the temperature around you. The atmospheric pressure will increase. When atmospheric pressure increases, the calibrated airspeed shown by your airspeed indicator will also increase. Correct? It will also increase. You may be flying at one same speed, but the indication shown to you will progressively keep on increasing because atmospheric pressure is increasing. Right? So in order, so I'm going to write here, as you descend, as you descend to lower and lower altitudes, atmospheric pressure increases. As you descend to lower altitudes, atmospheric pressure increases. Atmospheric pressure increases. As a result of this, your calibrated airspeed will also increase. Okay, because your calibrated airspeed will also increase. At higher altitudes, you're descending from higher to a lower altitude. So at higher altitudes, what happens? At higher altitudes, atmospheric pressure is lower. So in order to maintain a constant, so in order to maintain a constant calibrated airspeed, you have to increase, you have to increase your true airspeed. But now when you come down to lower altitudes, at lower altitudes, atmospheric pressure is already there. You have to decrease your true airspeed, maintain maintain to maintain a constant calibrated airspeed. Okay. If you do not do that, if you keep the true airspeed the same that was before, same as before at higher altitudes, your calibrated airspeed will increase. So at lower altitudes, if you want to fly at the same constant calibrated airspeed, you will have to decrease some other factor. Okay, you will have to strike a balance. If you want to maintain a constant calibrated airspeed, so decrease a true airspeed so that constant calibrated airspeed is maintained. Otherwise, calibrated airspeed will go on increasing. So correct answer is true airspeed decreases. How will Mach meter indication vary in a constant calibrated airspeed climb? So you are flying in a constant calibrated airspeed. So just now I told you when you are flying at a constant calibrated airspeed. So in this climb, you will encounter lower atmospheric pressures at high altitudes. Lower atmospheric pressures at high altitudes. Whereas at lower altitudes, you will get higher atmospheric pressure. Okay. So if you want to maintain a constant calibrated airspeed, okay, you will have to increase your true airspeed. Okay, to maintain. If you don't do that, if you fly at a constant true airspeed, what will happen to your calibrated airspeed? It will go on decreasing because as you climb to higher and higher altitudes, pressure decreases. And calibrated airspeed is a function of dynamic pressure. So if you are not surrounded by sufficient atmospheric pressure, so calibrated airspeed will also not be indicated to you properly, accurately. In order to make that happen, you will have to increase the true airspeed of your aircraft. When you increase true airspeed of your aircraft, you will artificially create that extra compressed pressure around the pitot tube so as to get the so as to get accurate calibrated airspeed indication. Okay, so you have to make that condition happen. If you rely solely on atmospheric pressure, that won't be adequate, that won't be sufficient because surrounding pressure is lesser, it's very low or very little, and therefore calibrated airspeed indication will be inaccurate. So you will have to increase another factor because there is a decrease in one factor, so increase some other factor in order to strike a balance, in order to counteract that. So to maintain a constant calibrated airspeed in a climb, increase your true airspeed. Increase your true airspeed. Now here they have asked what happens to Mach meter indication. What happens to Mach number? Now Mach number is equal to true airspeed divided by local speed of sound. True airspeed divided by local speed of sound. So if your true airspeed increases, the Mach number is directly proportional to true airspeed and inversely proportional to what? It is inversely proportional to local speed of sound. Correct? So if your true airspeed increases, what will happen to your Mach meter or Mach number indication? Your Mach number indication will also increase. So option A is the correct answer. Mach meter indications vary with speed and temperature, vary with speed only, vary with density and altitude. So the correct answer here is option Bravo. It varies with only with airspeed. Remember this fact. Now 2 points A and B are so and so nautical miles apart. True airspeed is given to you. On flight from departure to destination, headwind is minus 20 knots. So going outbound, you're getting a minus 20 knots headwind. Coming back, you are getting a headwind again. Correction, you're getting a headwind of plus 40 knots. So that means you're getting a tailwind actually. Plus 40 means a tailwind. What distance from departure is the point of equal time? Is the point of equal time. So we know that distance to point of equal time or critical point is total distance between A and Bravo, departure and destination, multiplied by homebound speed divided by outbound plus homebound speed. Now in this case, you are going from point A to point B. Here is your critical point. Now going outbound, your true airspeed is 490. Coming homebound, again the true airspeed is the same, 490, correct? Going outbound, you are getting a headwind of minus 20, minus 20. So if TAS 490, headwind minus 20, so ground speed outbound will be 490 minus 20, that is 470. Now coming back home, you are getting a headwind of plus 40 knots. So that means indirectly you are getting a tailwind of plus 40. Coming back home, this will become a tailwind. So ground speed homebound will be 490 plus 40, that is 530 knots. So let's substitute these values in the equation. Total distance between A and B is 1000. So 1000 into homebound speed 530 divided by outbound plus homebound. So 470 plus 530 is 1000. 1000, the numerator also you have 1000. So distance to critical point will be 530 nautical miles. 530 nautical miles. So option C is the correct answer. Question 30. Aircraft is over A at 16 evening 4 o'clock. It is flying direct to B, which is 3,000 miles away. TAS is given, winds are given. Outbound, when you are flying outbound, you are getting a tailwind of plus 55. When you are coming back home, you are getting a headwind of minus 75. Endurance is given. What is the distance from point A to the point of safe returns? So, this is your point A. This is your point B. This is point of safe return. So now your true airspeed is 390. So again, coming back home, your true airspeed is 390. Now going outbound, you're getting a tailwind of plus 55. You're getting a tailwind plus 55. Coming back home, you're getting a headwind of minus 75. So ground speed outbound will be 390 plus 55. Ground speed homebound will be 390 minus 75. Correct? So distance to point of safe return is endurance into outbound into homebound divided by outbound plus homebound. So endurance is 9 hours 30 minutes, 9.5. So substitute the values. So 315 plus 445 is 760. Numerator 9.5 into 445 into 315 divided by 760. So distance is 1752 nautical miles. So option Bravo. Simple. So with this, we'll stop here. I will do the next 10 questions in my next video lecture. I hope you have understood this many 10 questions that I solved. If you have any doubt questions, let me know in the comment box. I request you all to share this channel, this video with your friends. Subscribe if you haven't yet, and hit the like button if you have liked this video lecture. Thank you for your time.